Thank you, Professor, for giving me the floor. I'm Defo Jordan, a second-year PhD student from the University of Padova, and today I'll be speaking about the topological optimization of knee-brace frames for enhanced seismic performance using genetic algorithms. One of the major challenges in civil engineering today is earthquakes, which cause massive economic and human losses, as seen in the destruction of the Amatrice during the 2016 Central Italy earthquake and the collapse of steel buildings in the 1995 Kobe earthquake. As such, a key mitigation strategy involves structures that adhere to the capacity design principles, such as the knee brace frames, and these features has a strategic position for the knee element that provides a degree of ductility and true inelastic deformations, thereby preventing a brittle failure in the main load-bearing elements. So, the core problem we want to address here is that uniform brace placement in steel structures can sometimes be inefficient and uneconomical. And to avoid this, we seek a method to move from a suboptimal configuration to an optimal configuration that maximizes the energy dissipation. So, over the recent decade, the methods of optimal device placement have evolved from the sequential method, as you can see, and gradient-based approaches, which typically handle the limited discrete spaces. And for discrete problems with large number of variables, an exhaustive enumeration method actually becomes impractical because there is a vast search space. And as such, a suitable optimization method for this type of problem is the genetic algorithm, which is actually a self-adaptive method which is inspired from the principle of natural evolution. So, the genetic algorithm is basically initiated with a population of potential solutions using a fitness function, and the population evolves over successive generations through repeated genetic operators. That is, the selection is basically the step where we evaluate our different solutions to choose the best solutions, which have the potentiality to go to the next generation, just like the Darwin theorem of the survival of the fittest. And after that, you have the crossover and the mutation. And these generate the new populations, and the process continues until no further improvement is observed because we obtain our best individual. So our aim is actually to move from a suboptimal knee brace placement to an optimal topology of knee braces. And the model used for this is a 4-story 3-span knee braced orientations with 6 knee braces whose positions and orientations will be adjusted during the genetic algorithm process until we find an optimal topology. And our objective function here is actually the energy dissipated by the overall configuration. So, our numerical model is made based on the experimentally calibrated knee brace frames, which actually follows 2 experiments. The first experiment examines the structural behavior of the fuse under the 3-point bending frame, 3-point bending test, while the second investigates the structural behavior of a knee brace frame subjected to monotonic and cyclic loads. So, with respect to the result obtained from the experiment, the numerical model was developed in OpenSys with beams and columns modeled as elastic beam elements. The diagonal was modeled as the truss element. The link, or rather the knee element, was calibrated to capture the bending, the axial, and the shear behavior. And finally, the rotational and translational springs were incorporated to replicate the rail joint connections we observed during the experiment. So, as we mentioned earlier, the 2D link is developed in the OpenSys library calibrated in the normal and transversal direction. Actually, it follows a constitutive linear law governed by the stiffness of the fuse, while transversally, it follows a multicyclic law which is governed by the shear force, shear displacement behavior, from which we can observe the elastic, the hardening, and the plastic phase of our element. So, Our structural model, which is a 4-story, tree-based frame, is created in OpenSys, where time-series simulations are performed equally in OpenSys. And now the dynamic results there are then transmitted to MATLAB, where the genetic algorithm process takes place. And this generates actually a new topological input file, which is transmitted back to OpenSys for the analysis of the next topology in the OpenSys environment. Each of these topologies are actually what constitute an individual whose fitness is evaluated by computing its energy dissipated. And this is continued until the best topology is obtained. So, the genetic algorithm is initialized with a population of 50 individuals iterated over 20 generations. Each individual represents a frame topology defined by a presence and orientation matrix. The process incorporates 3 key constraints. One, we have a fixed number of braces, which is 6 in total. The second is at least one knee brace should be on the story because you want to prevent the soft story effect. And the third one is the orientation balance. You want at least 3 left-oriented and 3 right-oriented knee braces. Our MATLAB code begins by randomly placing 1 knee brace in each story, followed by a random placement of the remaining braces. The random placement of the remaining braces. Orientations are then assigned, and then the coded individual is rechecked to ensure that all the constraints are met. Next, each individual's fitness is evaluated, and then we follow the process we explained earlier. We have the selection process, actually a roulette selection process based on the performed fitness evaluation, and the crossover and the mutation process follows. Operators are then applied. Also, elitism is applied here to carry the best 5 individuals from the previous generation to the next generation. And after this iterative evolution through the generations, the optimal configuration is obtained. The genetic algorithm terminates after 20 iterations as shown in the convergence curve. This yields the optimal configuration, which is validated by its consistent reproducibility across runs, independent of variations of randomness in initial population, because we perform this tests a number of times and we obtain the same configuration. So the optimal configuration exhibits a higher total dissipated energy compared to the initial one. It also displays a uniform decreasing trend in dissipated energy from the base towards the top, which is actually a characteristic of optimal design according to the literature. So the optimal configuration allocates knee braces predominantly at the base of the building and in the outer base. And these findings align well with the literature, which highlights the effectiveness of placing dissipative elements in outer base of structures and at the base. The reason is actually straightforward. The base level experiences highest horizontal ground acceleration, so it needs to dissipate the most amount of energy. And additionally, during the directional reversals in earthquake, the outer base endure extra compressive and tensile stress due to the contributions from higher mode effects. And as you can see here, and that's normal that they actually are the most critical zones. Also, here we display the hysteresis loops of the knee braces in the optimal configuration. We have a quasi-similarity between the A and B, and this is due to because they have the similar orientation. They are both those of the first and second at the base, actually. While C and D have equal the same configuration, they are both left-oriented, yes. And this is because, okay, but left-oriented. It is true D is a little bit larger than C, but it's because he dissipates all the energy of the second level alone. So the uniform decreasing trend in energy dissipation of the optimal configuration towards the top aligns with the existing literature on optimal dissipative topologies, and moreover, the repeatable nature of these results, which is actually independent of the initial configuration, proves that actually validates its reliability. So in conclusion, the application of genetic algorithms through the interoperable use of OpenSys and MATLAB yields an encouraging result for topological optimization, and further work could explore taller frames and a multi-objective approach. Thank you for your attention.